Good morning, students. And now you are going to learn the Maxwell distribution, Maxwell Boltzmann distribution. You know, the distribution of molecular speeds is given by the Maxwell distribution. Okay, then already you have studied the kinetic theory of gas, and the gas molecules are rigid, always in random motion. And here question arises whether all the gas molecules they have the same velocity, and it is first shown by the Maxwell distribution law. And with the help of this you can study the what is root mean square velocity, what is average velocity, what is mean probable velocity. Okay, so we see the distribution of molecular speeds with the help of Maxwell-Boltzmann distribution law. You know, the kinetic molecular theory of gases. A gas contains large number of particles in a rapid motion. Each particle has a different speed, and each collision between particles changes the speed of the particles. And understanding of the properties of the gas requires understanding of the distribution of particle speed. Here, the many molecules and many velocities. At temperatures above absolute zero, all molecules are in motion. In case of gas, this motion consists of a straight line jumps with whose lengths are quite great compared to the dimensions of molecule. Although we can never predict the velocity of a particular individual molecule, the fact that we are usually dealing with a huge number of them allows to know what fraction of molecules have kinetic energies that lie within the given range. The trajectory of an individual gas molecule consists of a series of straight line paths interrupted by collisions. What happens when two molecules collide depending on their relative kinetic energies? In general, a faster or heavier molecule will impart some of its kinetic energy to a slower or lighter one. These molecules having identical masses and moving in opposite directions at the same speed will momentarily remain motionless after their collision. If we could measure the instantaneous velocities of all the molecules in the sample of a gas at some fixed temperature, we would obtain a wide range of values. A few would be zero and few would be very high velocities, but the majority would fall into a more or less well-defined range. We might be tempted to define an average velocity for a collection of molecules, but here we would need to be careful. The molecules moving in opposite direction have velocities of opposite signs because the molecules are in the gas are in a random thermal motion. There will be just about as many molecules moving in one direction as in opposite direction. So the velocity vectors of opposite sides would all cancel and the average velocity would become out 0. Since this answer is not very useful, we need to do our averaging in a slightly different way. The proper treatment to average the squares of the velocities and then take the square root of this value. The resulting quantity is known as root mean square velocity. I repeat, the average the squares of velocities and take the square root of this value. The resulting quantity is known as the root mean square velocity. It is also abbreviated as RMS, means root mean square velocity. And the root mean square velocity, it is the square root of average velocity square divided by n number, where n is the number of molecules in a system. The formula relating the RMS velocity to the temperature and molar mass is surprisingly simple, considering the great complexity of events it represents. Here, RMS velocity, it is given by square root of 3RT upon m, where m is the molar mass in kg per mole and r is the gas constant. Here, the RMS velocity, it is also given by 3 kb into T upon m, where m is the molecular mass in kg and kb is the Boltzmann constant and is just the gas constant per molecule. Therefore, we can write the Boltzmann constant kb, it is equal to R upon Na, it is equal to R upon 6.02 into 10 raised to 23. That is the Avogadro number. And here example is there to find the RMS of root mean square velocity of a nitrogen molecule at 300 Kelvin. You know, the molar mass of N2 gas, or a molar mass of N2 gas, it is 28.01 gram per mole. Substituting in the above equation and expressing R in energy units, we obtain here velocity square, it is equal to 3 into R value 8.31 joule per Kelvin per mole per Kelvin, and T here it is temperature 300 Kelvin upon molar mass, that is the 28.01 into 10 raised to minus 3 kg per mole, and it should become 2.67 into 10 raised to 5 joule per kg. Then recalling the definition of the joule, here joule, it is equal to 1 kg meter square into second square, and taking the square root, here we have velocity V, it is equal to square root of 2.67 into 10 raised to 5 into joule per kg into 1 kg meter square into second square upon 1 joule, and it becomes equal to 517 meters per second, and we convert it into kilometer per second, it becomes equal to 1860 kilometer per hour. Okay, here the unit of V, it is in meter per second, T is in the absolute temperature, and M, it is a molar mass in grams. So, the Boltzmann distribution law. If we were plot the number of molecules whose velocities fall within a series of narrow range, we would obtain slightly asymmetric curve known as velocity distribution. This peak of this curve would correspond to the most probable velocity. This velocity distribution curve is known as Maxwell-Boltzmann distribution, but is frequently referred to as Boltzmann name. The Maxwell-Boltzmann distribution law was first worked out around 1850 by the great Scottish physicist James Clerk Maxwell, who is better known for discovering the laws of electromagnetic radiation. Later, the Austrian physicist Ludwig Boltzmann put the relation on sounder theoretical basis and simplified the mathematics somewhat. Boltzmann pioneered the application of statistics to the physics and thermodynamics of matter and was an ardent supporter of the kinetic theory of matter at a time when it was still not accepted by many of his contemporaries. The Maxwell distribution is used to determine how many molecules are moving between the velocities phi and phi plus dphi. Okay, the Maxwell-Boltzmann distribution is used to determine how many molecules are moving between the velocities phi and phi plus dphi, assuming that the one-dimensional distributions are independent of one another and the velocity in the y and z directions does not affect the x velocity. For example, the Maxwell-Boltzmann distribution is given by dn by n, it is equal to m by 2 pi kb into t raised to 1 half into exponential raised to minus mv square upon 2 kb into t into dv. This is the Maxwell-Boltzmann distribution law, and dn by n is the action of molecules moving at a velocity phi plus dphi. M is the mass of the molecule, Kb is the Boltzmann constant, and T is the absolute temperature. The function can be written in terms of scalar quantity speed phi instead of the vector quantity. This form of function defines the distribution of gas molecules moving at different speeds between phi1 and phi2. Thus, we can write f of phi, it is equal to 4 pi phi square into m by 2 pi kb into t raised to 3 by 2 exponential in raised to minus mv square upon 2 kb t. The Maxwell-Boltzmann distribution can be used to determine the distribution of kinetic energy of a set of molecules. The distribution of kinetic energy is identical to the distribution of speeds for certain gas at temperature. The Maxwell-Boltzmann distribution is probability distribution, and just like such any distribution can be characterized in a variety of ways, including the average speed is the sum of the speeds of all particles divided by number of particles. Here, average speed, it is the sum of the speeds of all the particles divided by the number of particles. Then, the most probable speed is the speed associated with the highest point in the Maxwell distribution. I repeat, the most probable speed is the speed associated with the highest point in the Maxwell distribution. Only a small fraction of particles might have this speed, but it is more likely than any other speed. Then the width of the distribution. The width of the distribution characterizes the most likely range of speeds for the particles. One measure of the width is the full width at half maximum. To determine this value, find the highest height of the distribution at the most probable speed, and this is the maximum height of the distribution. Divide the maximum height by 2 to obtain the half height and locate the two speeds in this distribution that have this half height value. On speed will be greater than the most probable speed and other speed will be smaller. The full width is the difference between the two speeds at the half maximum value. Then the velocity distribution depends on temperature and mass. Remember, the velocity distribution depends upon temperature and mass. Higher temperature allow a larger fraction of molecule to acquire greater amount of kinetic energy, causing the Boltzmann plots to spread out. This is the figure shows how the Maxwell distribution is affected by temperature. Here in this diagram they have given the Maxwell distribution. So we will see the next point later on.